Hi, today we're going to be starting with Cambridge Chemistry, Paper 1, Multiple Choice, May June 2024, Paper 11. And the grade threshold for this paper was 27 out of 40 to get an A. So, let's get started with this paper. Okay, the first question says that a scientist heats a sample of a liquid. Okay, we have a liquid and we are heating it. The scientist measures the temperature of the sample and plots a graph of temperature against time. Okay, we have temperature on our y-axis, we have time on our x-axis. What's happening is over here, W, this substance is a liquid. And now we're heating a liquid, so the temperature is increasing. Okay, over here the temperature was 15 degrees Celsius, for instance. And over here the temperature was 20 degrees Celsius. So the substance is being heated, the temperature is increasing, and over here from X to Y, what's happening? The line has become flat. And what does a flat line tells us? What do you guys think a flat line tells us in a cooling or a heating curve? It tells us that the temperature basically stopped increasing. The temperature line has become flat. The temperature has become constant. There's a constant value for temperature, though the time is increasing. From over here, for example, 20 seconds to 30 seconds, time is increasing, but temperature is not increasing. Why? Because the state of the substance is changing. For sure, the substance is a liquid initially, so now from X to Y, the substance is basically changed from a liquid to a gas. Okay, so it's basically not increasing temperature, but what's happening is the energy you are supplying to it is basically used to turn the liquid into a gas, and after becoming a gas the temperature again rises and it increases. And basically what happens when your temperature is increasing, you need to understand that when you're increasing the temperature, what happens is the kinetic energy of the particles, which is basically the energy for the movement of the particles, okay, how fast or slow your particles move, it basically increases. So you are basically increasing the kinetic energy, and as you increase the kinetic energy of the particles, the thermal energy or the temperature also increases. Okay, which statements are correct? Between points W and X, the temperature increases and the particles move faster. Between points W and X, okay, that's correct. The temperature is going to increase because we can see the line is going up and the particles going to move faster. You know, whenever you increase temperature, you increase the kinetic energy, the particles move faster. This is going to be absolutely correct. Moving on to statement 2, which says between points X and Y, there is no change in the temperature because the energy is needed to change the liquid into gas. That's what I told you. Look, the line is flat over here for the temperature. For example, if this was 50, for instance, I say this is 50 degrees Celsius, it remains 50 for the entire line. For the entire time period from X to Y, it remains 50. That 50 does not change. It does not rise or decrease. What's happening is basically that liquid is turning into a gas. That's why it remains constant. And because energy is needed to change the liquid to gas, that's correct. What basically happening is you are changing the arrangement of the particles. So that's why the temperature does not increase between state changes. Always remember, for example, if your liquid is turning into a gas, or your gas is turning back into a liquid, or your solid is turning into a liquid, whenever the state of the substance is being changed, it's going from one state to another, the temperature does not rise or fall. It remains constant, though you continue to supply the energy. Okay, between points Y and Z, the particles move further apart. Okay, between points Y and Z, the particles move further apart. That's going to be correct because the temperature is being increased. So that means the kinetic energy of the particles increasing. That means the particles moving further apart from one another because the kinetic energy is increasing. They're moving faster. So that's going to be also correct. The motion's going to of the particles going to increase. So 1, 2, 3 all are correct. So that's going to be option A. Moving on to the next question, which says a sample of substance X contains iron and sulfur only. Okay, now the important thing is only. Only means there is no other substance apart from these two, iron and sulfur. Okay, a substance consisting of two things, iron, sulfur only. Okay, the AR of iron is given, the AR of sulfur is given. That's going to be useful. I don't know where, but let's see where do we use them. In which row is it possible for both statements about X to be correct? Okay, we have a statement 1 and we have a statement 2, and what we need is that both the statements need to be correct. Okay, let's see. X is a mixture with the ratio 4:7 by mass of iron and sulfur. Okay, and X is a compound with the ratio 4:7 ratio by mass of iron ratio sulfur. Okay, now what's basically happening over here is, if you cannot process it because it's a little difficult to understand. Over here they're talking about X is a mixture. Over here they're saying that X is a compound. in the first statement, they say that the ratio is 4:7 of iron ratio sulfur. And over here, again, they say it's 4:7 for iron ratio sulfur. Now, what's basically happening, you need to understand is that, look, 4 is the ratio of your iron and 7 is the ratio of your sulfur. Over here, 4 is the ratio of your iron and 7 is the ratio of your sulfur. Okay, that's the first statement. Okay, now let's move on to the second one. The second statement says X is a mixture. Again, it's a mixture with the ratio 7:4. Now they've flipped the ratios. Over here it was 4:7. It's over here it's 7:4. By mass of iron ratio sulfur, and X is a compound. Again, a compound with the ratio 7:4 by mass of iron and sulfur. Okay, don't be intimidated or confused by the statements. Now simply they flipped the ratios. That's all they've done. It was 4 iron, 7 sulfur. Over here it's 7 iron and 4 sulfur. So 7 is the ratio of iron and 4 is the ratio of sulfur. 7 is the ratio of iron, 4 is the ratio of sulfur. Again, they've told that over here X is a mixture, over here X is a compound. Moving on, X is a mixture with the formula FeS. Okay, let's see about it. Mixtures don't usually have formulas, so that's incorrect. Mixtures cannot have like formulas like these, so not correct. And X is a mixture with the formula FeSO4. Oh wow, that is extremely incorrect because there is an oxygen over here, and in the first statement they said that X only contains iron and sulfur. Only means this oxygen cannot be present, so we just simply cross out the statement. It cannot be correct, not correct. And this one's also correct, not correct. Now let's see between A and B. So now we have iron Fe ratio sulfur. So what's the AR of iron? It's 56 ratio 32. So now what's simply happening is you know that in ratios, if you guys have studied maths, you know that we can simply just divide it. Like we can write 56 upon 32. This is going to be iron ratio sulfur. So we just have to find the ratio in the simplest terms. Okay, so let's see what's 56 divided by 32. That's going to give us the ratios. Let's see if we get 4:7 or we get 7:4. So 56 divided by 32. So 56 divided by 32. What do we get? We need okay, we get 7:4. You can see over here that we simply get 7:4. In fraction, we get a 7:4. That tells us that the ratio is going to be 7:4. 7 is the ratio for iron and 4 is the ratio for sulfur. So you just had to look at this fraction at the top on the calculator, that it's 7:4. So it's going to be option B because we get a 7:4, not a 4:7. That's incorrect. Okay, and secondly, in compounds and in mixtures, you can have ratios. In compound, you can have formulas as well, but in mixtures, you don't have formulas. So that was incorrect. And with that, we move on to our next question, which says that the chlorine atom Z has a nuclear number of 37. What is a nuclear number? A nuclear number is simply your number of protons plus your number of electrons. What basically happens is, this is your atom. This is the nucleus. And these are the shells around the nucleus. In the nucleus, you have your protons and your neutrons. So the total number of things that's inside the nucleus are known as your nucleons. A nuclear number is basically the mass number and the number inside the nucleus. Which row is correct? Number of neutrons in Z. So what are going to be the number of neutrons? Number of neutrons are going to be obviously the total number of this thing minus the number of protons. You're going to get the number of your neutrons. So a chlorine atom, so we know which kind of atom we are dealing about. We are dealing about a chlorine atom. Always remember that the proton number of an atom can never change. Okay, it's the identity of that atom unless you have an alpha beta emissions. Okay, that's nuclear physics. That's not in chemistry. In chemistry, the identity of your atom, if it's a chlorine atom, it's always going to have a fixed number of protons. It can have a different number of electrons because it can form a chlorine ion, but what is not going to change is the number of protons. So the number of proton remains fixed. We're going to check the number of protons from the periodic table, and from this is the nuclear number, the total number. From 37, we're going to subtract the number of protons, so we get the number of neutrons. So number of protons in a chlorine atom. So simply on the periodic table, this is a chlorine atom. 17 is the number of your protons. And over here, please don't be confused. Don't take this neutron, mass number or the nuclear number. This is also the mass number. Over here, above, they've told you it's 37. So you just don't, try to outsmart the examiner and take 35.5. Otherwise, it's going to be wrong. Okay, because above they've given you, but 17 you can take from here because that's going to be fixed, but this number below can change. Why can change? Because this is the relative atomic mass and the above one is normal mass. Okay, it's normal mass of a single chlorine atom. This is the relative atomic mass of all the isotopes combined. Okay, you need to understand this because your neutron number, it cannot be 0.5. So why there's a 0.5 upon here? You need to understand this is the relative atomic mass you get after adding the mass of all the isotopes. So 17 we are going to take and we're going to subtract 37 minus 17 going to give us the neutron number that we need. 37 minus 17. 37 minus 17. That's going to give us 20. So 20 is the number of neutrons we need and number of electrons in the second shell of Z. Okay, so now we know that Z is going to have 17 protons. And because Z is an atom, it's not an ion. Very important thing over here, it's an atom. An atom means that equal number of protons and electrons. That means if it has 17 protons, it's going to have 17 electrons as well. So let's draw the 17 electrons. The first shell going to have 2 electrons. The second shell is going to have 8. 1, 2, 3, 4, 5, 6, 7, 8. And because we have to do a total of 17, we have to add more. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We've drawn 18. I guess we've drawn just one more. We need to erase this one right here. And we are done with our 17 electrons. So now, how many electrons do we have in the second shell? This is the first shell. This one's the second. In the second shell, we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 is going to be the correct answer. That makes it option D. Okay, this was easy, I guess. Moving on to the next question, which says, which particles are isotopes of the same element? What did I just told you? If the element is the same, that means it's going to have the same proton number. Proton number is basically the identity of that element. Okay, if two elements are same, it is impossible for them to have different proton numbers, because if the proton number changes, the element changes, the identity of the element changes. So these two elements are the same because they have the same proton number, and these two elements are same because they have the same proton number. Okay, we have to look for isotopes. Okay, let's see the definition of isotope. What is an isotope? Isotopes basically have same proton number, but they should have a different neutron number. Okay, we need and electrons have nothing to do in isotopes, so we don't look at this electron column. We only are considerable about protons and neutrons. So we need different neutrons. We have got the same protons, now different neutrons. But over here we have same protons, 28 and 28. These cannot be isotopes because they have the same number of neutrons. For it to be an isotope, we need different number of neutrons. So Y and Z are going to be isotopes because they have different neutron number. 30 and 28 are obviously different and same proton numbers. So the two isotopes over here are going to be Y and Z. Why? Because of these different number of your neutrons. Moving on to the next statement, question which says statements about graphite and silicon IV oxide are given. Okay, which statements are correct? What do I know about graphite and silicon IV oxide? I know both of them are giant covalent substances. Both of them are going to have high melting and boiling points. Graphite is going to conduct electricity because graphite has layers, and moreover graphite has a fourth unbonded electron that is delocalized, that can move through the layers of graphite. Okay, and silicon IV oxide cannot conduct electricity. Moving on, which statement is correct? Silicon IV oxide is found as an impurity in iron ore. That's extremely correct. The first statement I found, and it's correct. Why it's correct? Because you should know that in iron ore we basically have silicon IV oxide, which is the main impurity. That's the sand particles in iron, and you basically react this impurity with your calcium oxide to form calcium silicate, CiSiO4, which is commonly known as your slag. So that's correct. Okay, the angles between the atoms, let's read other statements for the sake of, perfection. The angles between the atoms of silicon IV oxide and graphite are same. That's incorrect. In graphite, we have three-dimensional hexagonal rings, something like this. Whereas in silicon IV oxide, we don't have hexagonal rings. The structure is something like this. ठीक है? The silicon and oxygen atoms are connected together by strong covalent bonds, and it's a 3-dimensional tetrahedral structure. And for graphite, it's hexagonal rings. Okay, see, the melting points of silicon ionic oxide and graphite are high because ionic bonds are stronger than covalent bonds. That's incorrect. We don't have ionic bonds. We only have covalent bonds. When graphite acts as a lubricant, the covalent bonds between layers are broken. That's extremely incorrect. What happens is the intermolecular, this is one layer of graphite, this is another layer of graphite. Between the layers of graphite, you have your intermolecular forces of attraction. You have your weak IMF. And basically, when you are making the layers slip over each other, you're not breaking the bonds. What's happening is the weak IMF, the weak intermolecular forces of attraction are being broken. And that's why it has the layers can slip over each other and it can be used as a lubricant. Moving on, that's also incorrect, okay? Because when you break the covalent bonds, you're melting graphite, okay? And that's gonna require a very high temperature. 6, which says statements about empirical and molecular formula are given. Okay, what's empirical formula? Empirical formula is the simplest whole number ratio, and molecular formula is the total number of molecules that are present, okay? So which statements are correct? The empirical and molecular formula of a compound are always different. They can be same. They can be same. For example, I give you an example of C23 H25 and O6. What do you guys think? What's the empirical formula of this compound? It's going to be the same as the molecular formula. Why? Because it cannot be cut down. You cannot cut it on any table. So they can have the same empirical and molecular formula if they cannot be cut down. If that's the simplest whole number ratio, the molecular formula itself. So the empirical formula of ethine, C2H2, and of benzene, C6H6, are the same. Oh, that's correct. Because look over here. If you cut this 2 and this 2, it becomes CH. And if you cut this 6 and this 6 on the table of 6, it becomes CH. So that's correct. The empirical formula for both of them are going to be the same. You had to understand this. How do you make empirical formula? C2H2. You basically cut both the numbers on one table. So it cuts on the table of 2. 2 1 times 2, 2 1 times 2. That makes it CH. Another C6H6. You cut it on the table of 6. 6 1 times 6, 6 1 times 6. And it becomes CH. So that's going to be correct. Let's not read the other statements and waste our time. Moving on. What is the relative formula mass of aluminum oxide? Okay, I guess the difficult part over here was not finding out the relative formula mass, because that's going to be easy. And one important thing over here, why do you think they said formula mass? Why did the examiner not use the word of molecular mass? Because that could also be used. The reason for that simple. Aluminum oxide is your ionic compound, and for ionic compounds you use the word formula mass, not molecular mass. Molecular mass is used for molecules, and formula mass is used for ionic compounds, because in ionic compounds you don't have molecules. So for aluminum oxide, you need to realize that aluminum has a charge. I guess that's the thing people most struggle with. Has a charge of 3+, and oxygen has a charge of 2-, and this 2 comes over here, this 3 goes down over here, and what you make up forming is Al2O3. So that's your aluminum oxide. That's the formula. And now you have to calculate the formula mass. You know, for aluminum, I guess it's 27. So we have 2 aluminums, 27 times 2. Oxygen is 16. So we have 3 oxygen, so 16 times 3. And let's see what that gives us. 27 times 2 plus 16 times 3. That's going to give me 102. 102, and which makes it option C to be correct. Moving on, how many ions are there in 16 grams of anhydrous copper 2 sulfate? Okay, so now they're asking about ions and how many ions are present in this particular mass. One thing you got to realize that, look, how many ions are there? For example, if I ask you, if I have copper sulfate, CuSO4, and if I dissociate this copper sulfate like this, how many ions am I going to have? I'm going to form 1 mole of copper ions and 1 mole of my sulfate ions. Okay? That's what you got to know. From 1 mole of copper sulfate, you can form 1 mole of copper ions and 1 mole of sulfate ions. And in total, from 1 mole of copper sulfate, you can form 2 moles of ions. Okay? that's what was, I guess, most confusing for people, that from 1 mole of an ionic compound, you can form 2 moles of the ions that's making it. Okay, over here, from 1 mole of aluminum oxide, how many ions do you think you can form? You can form 2 moles of aluminum ions and 3 moles of oxygen ions, because you have O3. From 1 mole of Al2O3, you can form 2 moles of aluminum ions, 3 moles of oxygen ions. From 1 mole of copper sulfate, you can form 1 mole of copper ions, 1 mole of sulfate ions. Okay, that's how I could explain this. Now, we have to find the moles in copper sulfate in 16 grams. Moles equals to mass upon mr. Mass is 16 mr. Copper is 64, I guess. Plus sulfur is going to be 32. And plus oxygen is going to be 16. So it's going to be 16 times 4. And let's calculate this. 64 plus 32 plus plus 32 plus 16 times 4, and that's going to give me 160. So 160 is the mr of this compound, so 16 upon 160, mass upon mr, that's going to give you your mole. 16 divided by 160 and 0.1, so you have 0.1 moles of your copper sulfate. Now the important thing, you have the moles of your copper sulfate, and you know that in 0.1 moles of copper sulfate, how many moles of ions are you going to have? देखें, in 1 mole you have 2 moles of ions. ये तो समझ आ गया ना कि इसके 1 मोल में इसके 2 मोल्स होंगे आइंस के. 1 मोल होएगा कॉपर आइन का, 1 मोल होएगा सल्फेट आइन का. In 1 mole of copper sulfate you have 2 moles of ions. So basically in your 0.1 moles of copper sulfate, how many moles of ions are you going to have? X moles, and the value of X is going to turn out to be 0.2. So you have 0.2 moles of your ions. Now simple formula for this is that number of particles, I guess this formula is extremely beneficial. Number of particles upon your Avogadro's constant, which is 6.02 into 10 exponent 23 equals to your moles. Okay? Number of particles can be anything. It can be ions, it can be molecules. Right now we're dealing with ions. So moles, we have 0.2 moles. And this thing right over here comes over here, gets multiplied with the moles, and you get the number of ions. So 0.2 multiplied by 6.02 into 10 exponent 23 gonna give you your number of particles. Let's figure it out. 0.2 multiplied by your Avogadro's number. So your 0.2 multiplied by 6.02. How do I get the exponent thing? 10 exponent where to get the exponent thing? In a normal calculator, it's usually over here above the answer thing, but over here I guess it's difficult to find. How to get it? I guess I might figure it out sometime later, but what we can do over here right now is we can just simply go to a simple calculator and multiply this thing right over here. This thing, we can simply multiply this, and this power remains the same. So 6.02 multiplied by 0.2. So 0.2 multiplied by 6.02, and that's going to give me 1.204. So and luckily that's in standard form. 1.204 into 10 exponent 23, that remains the same. So that's going to be my answer. 1.204 into 10 exponent 23. Don't be confused by this and this. These two options seem exactly the same, but over here this 24 is going to ruin your answer. It's 10 exponent 23. So you got to be careful while choosing the options. You got to see these things. Okay, and these are just distracted options. I would say that if you're a little careless and a little less able to see, you're going to be distracted. Moving on, what sample contains the most atoms? Okay, we have to look for the most amount of atoms. One thing we know, we have water, we have carbon dioxide, we have methane, and we have hydrogen chloride. I guess we require no calculation for this. Why? Because you simply just have to figure out the formula for water. The formula for water is H2O. The formula for carbon dioxide is CO2. The formula for methane is CH4. And the formula for your hydrogen chloride is going to be simply HCl. HCl. Now, what do you think? We are looking for the number of atoms. How many atoms do we have in H2O? Just figure out. 2 atoms of hydrogen, 1 atom of oxygen. Okay, we have 2 atoms of hydrogen and 1 atom of oxygen in H2O. So a total number of 3 atoms. How many atoms of total atoms do we have in carbon dioxide? We have 1 atom of carbon and 2 atoms of oxygen, a total of 3 atoms over here as well. So it's going to be 3. And in methane, we have 4 hydrogen atoms and 1 carbon. That makes a total of 5 atoms. In hydrogen chloride, we have a total of 1 hydrogen atom, 1 chloride atom. That makes it a total of 2 atoms. Okay, we have the number of atoms. Now we know that in 1 mole of water, we are gonna have a total of 6.02 into 10 exponent 23 water molecules, H2O. And to get the atoms, we multiply this number by 3. Okay? Because there are 3 in 1 molecule. Over here we have 0.5 moles, over here we have 1 mole. Obviously this is going to be greater because दोनों के एक मोल में equal number of atoms होंगे, और इसके 0.5 मोल हैं तो इसके half atoms होंगे, इसके उससे double atoms होंगे. और इधर 2 moles of hydrogen chloride में इसको बस आपने multiply कर देना है 2 से. So 2 times equal to is going to be 4, which is still less than 5. So it's going to be 5. 5 is going to be the greatest number of atoms you have. What you do is simply multiply this number by this. 3 multiplied by 0.5 gives me 1.5. Okay? 3 multiplied by 1 gives me 1.5. It gives me 3. 5 multiplied by 1 gives me 5. 2 multiplied by 2, I'm just multiplying this number with the number of moles. 2 multiplied by 2 gives me 4. The highest number is over here, so 5 is going to be my answer. Okay, that was simple. I guess you just had to multiply the number of atoms with the moles to get the answer. And if you have to get the total number of atoms, then you multiply this with first the moles and then with 6.02 into 10 exponent 23, but that's a lengthy working. Over here, I guess that's the fittest way to do it. Moving on to question number 10, which says the reaction shown all produce hydrogen. Okay, all reactions are giving us hydrogen in some way or the other. Which reaction produces the greatest volume of hydrogen measured at RTP? Okay, we have to figure out that which reaction will give us the greatest volume of hydrogen. Now we know that hydrogen is a gas, and for gases we have a formula. What's the formula? We can simply just revise it, that moles equal to your volume upon 24. That's the formula, DMQ, to get moles or either the volume of hydrogen, and we have to figure out the greatest volume of hydrogen. Okay, we have 1.4 gram of carbon reacts with excess steam. Steam is in excess, we cannot take the moles of steam, therefore. Okay, how many moles are going to we have for carbon over here? 1.4. Okay, that's the mass divided by the MR of carbon, which is going to be 14. 1.4 divided by 14, that gives me 0.1 moles. So 0.1 moles of carbon. And over here, I always tell you, I guess that's the best tip I can ever give to you guys, that whenever you have equations like this, what do you do? The first step is to look at the coefficient. These coefficients are the most important thing you can have in any equation. They tell you about the molar ratio. They tell you about how many moles of one thing are going to react with how many moles and how many moles are going to be produced. So these things are very important. So this equation right over here tells me that 1 mole of carbon going to form 1 mole of hydrogen gas. So 0.1 moles of carbon is going to form 0.1 moles of hydrogen gas. Okay, so over here I have calcium hydride, and I have how many moles of calcium hydride? The mass of calcium hydride is 2.4. The MR is going to be calcium is 40 plus 2, 42. So 2.4 upon 42, let's figure it out, divided by 42. I have 0.0571. Okay, I have 0.0571 moles of calcium hydride. And look at the molar ratio. The molar ratio is 1 mole of calcium hydride forms 2 moles of hydrogen gas. So now these moles are also going to be multiplied by 2 to get the moles of your hydrogen gas. So these moles right here get multiplied by 2, and I have 0.114. So I have 0.114 moles of hydrogen gas over here. I hope you get how I'm doing it. Now we have simple calcium that's reacting with excess dilute hydrochloric acid. Whenever you have something in excess, you cannot take its moles to get the moles of your product, because that thing is not totally being used up in the reaction because it's in excess. So now 1 mole of calcium is going to form 1 mole of hydrogen gas. And how many moles we have of calcium over here? 4 is the mass. The MR of calcium is 40, and I guess that's going to give me a 0.1. So let's do it. 4 divided by 40, 0.1. Okay, if you have 0.1 moles of calcium, how many moles of hydrogen? Same moles, because the molar ratio is same, 1:1. Okay, over here we have how many moles of zinc? 50 cm cube of 2 mole per dm cube sulfuric acid with excess zinc. Zinc is in excess, so now we cannot take the moles of zinc, we have to take the moles of sulfuric acid. Moles equals to simply your volume into your concentration. Volume is 50 cm cube, but it's in cm cube. We take the volume in dm cube divided by 1000 times my concentration, which is 2, and 50 divided by 1000 multiplied by 2. That's again gonna give you a 0.1 mole of your sulfuric acid, and the molar ratio is 1:1. If 0.1 mole of sulfuric acid, then how many moles of hydrogen gas? Is 0.1 mole of hydrogen gas. So clearly over here we can see that we have 0.1 mole of hydrogen gas, 0.114 moles of hydrogen gas, 0.1 mole of hydrogen gas, and 0.1 mole of hydrogen gas. Clearly, in which option do we have the highest moles of hydrogen gas? This option. So that means that's going to yield us the highest volume, and because the mole ratio equals to your volume ratio, so it's clearly going to be option B. I guess that was a bit lengthy, but you had to understand the concepts of your mole ratios, that how in an equation the ratios are all connected. Moving on to the next question, which says that 4 solutions of NaOH are made by dissolving solid NaOH in water. Okay, you have 4 solutions that you're making. You have your solid NaOH and you are dissolving it in distilled water. Which method makes a solution with the concentration of 0.1 mole per dm cube? Okay, now you are given with the concentration that is your ideal concentration that you want, and now you have a different kind of things given and you have to figure out the concentration. So what's the formula for concentration? I know that simply concentration equals to my moles upon my volume. I have my volume in each solution, and for moles, what do I have to take? I have to take this mass which I am given with. So simply let's figure out the mass, the moles we are going to get. It's going to be simple. We just have to divide the mass from with mr. So moles equal to mass, which is 1.6 upon mr, which is 40. And for this one, it's going to be 3.2 divided by 40. For this one, it's going to be 4.0 divided by 40. For this one right here, it's going to be 8 divided by 40. I hope you understand what I'm doing over here. I'm simply taking the mass, I'm dividing it by the mr of NaOH to get the moles, and after I get the moles, I'm going to plug in my moles over here divided by the volume, which is given over here, to get my concentration. So 1.6, 3.2, 4, and 8. Okay, 1.6 divided by 40, that's going to give me 0.04 moles. For this, I get 0.04 moles. Then 3.2 divided by 40, 0.08 moles. 0.08 moles. For next, it's 4.0 divided by 40, which gives me 0.1 moles. 0.1 moles. And next I have 8.0 divided by 40, which gives me 0.2 moles. 0.2 moles. Okay, now I have the moles. I simply now have to divide my moles with my volume, but I have to be sure of one thing. I need the volume in dm cube. Over here I am given with all volumes in cm cube, so I first have to divide my volume by 1000 to make it in dm cube. So simple, you can do it on calculator as well, and you can do it simply as well. What you're gonna do to convert this to dm cube, simply just move the decimal 1 2 3. That's gonna make me 0.4 dm cube. This one's gonna make me 0.25 dm cube. This one's gonna make me 0.1 dm cube and 0.5 dm cube. So now it's gonna be moles upon volume. Moles this, volume this. 0.004 divided by 0.4. So let's do it. 0.004 divided by 0.4, which gives me 0.01. 0.01. Okay, that's my price. I just have to keep my eyes on the price. This is 0.01. Now these moles divided by this volume. 0.08 divided by 0.25. Okay, 0.08 divided by 0.25, 0.32 moles, concentration 0.32. Now 0.1 divided by 0.1, that's going to give me 1. Now 0.2 divided by 0.5. Okay, 0.2 divided by 0.5 gives me 0.4. Okay, 0.4 mole per dm cube. Okay, so I just figured it out. This I've written wrong. It was not this. It was, I just divided 0.04 divided by 0.4 gives you 0.1 mole per dm cube. So I have got all my concentrations, and out of all my concentrations, A matches my answer. So it's gonna be option A, which is gonna be correct. Moving on to the next question, which says that which row shows the substances that can be electrolyzed. To electrolyze a substance, what do I need? To electrolyze a substance, I need it to be in liquid form. Okay, I need it to be in a form that's firstly liquid. I cannot electrolyze a solid substance. And second thing I need ions, because if my ions are going to move, that's how I can figure out what's making going at my anode, what's going at my cathode, and my ion should be moving. So aqueous sodium chloride, firstly it's aqueous, it's in a liquid form, and secondly it has sodium and chloride ions, so definitely I can electrolyze it. Copper is a solid, I cannot electrolyze it. Graphite is a solid, I cannot electrolyze it, though graphite electrodes can be used as my electrodes in the electrolysis, but it cannot be itself electrolyzed until it's molten. Okay, or until ions can move in it, and graphite definitely has no ions. Molten lead to bromide, it's molten, it's in liquid form, and it has ions, so I can definitely electrolyze it, and which makes option B to be my correct option. Moving on, the apparatus shown is set up to electroplate a steel key with copper. Okay, now one thing I know for sure, that when I have to electroplate a substance, I keep that substance on my cathode, and the substance with which I have to electroplate it, like copper, I keep it at my anode. So this is my negative, this is my positive. Negative is going to be my cathode, and positive is going to be my anode. Okay, now what have they done over here? They've placed the key on the anode. That's incorrect. The key had to be placed at the cathode because it is what has to be electroplated, and the copper at the anode. I don't know why that's incorrect, but let's see what the question says. The key does not get coated with copper. Okay, that should be the case because they have just placed it the wrong way. Which change needs to be made to electroplate the key? Increase the concentration of aqueous copper to sulfate. That's not going to work. What's the problem over here is that anode and cathode have been shifted, so this cannot be simply corrected by increasing the concentration. Increase the electric current. Okay, that's not going to make it correct. We need proper anode and cathode thing. Okay, replace the solution with dilute sulfuric acid. No, all of this is just doing with the solution thing or the current thing, but nothing is dealing with the anode and cathode. Reverse the electrical connections. Oh, that's the correct one, because when you reverse the electrical connections, what's going to happen is that this one is going to become your negative, this one's going to become your positive, and then finally on the negative you have the key. At the negative, which is the cathode, you're going to have the key, and at the positive, which is the anode, you're going to have copper. And so option D is going to be the correct one. Moving on, ammonium nitrate dissolves in water. Okay, we know why does it dissolve, because all nitrates are soluble and all ammonium salts are as well soluble. It should for sure dissolve, and we can see that it's a endothermic reaction. Which statements are correct? The process is endothermic. Okay, that's correct because it's a positive enthalpy change. This positive sign right here tells us that it is going to be endothermic. The water gets colder during the process. Okay, Now, one thing that you should know that whenever you're doing endothermic reactions, for example, this is your ammonium nitrate and you're dissolving it in your water. What's going to happen is that after the reaction, the water is going to get colder. Why? Because in your endothermic reaction, the heat energy is absorbed from the surroundings. So the surroundings get colder. Okay? Just think of it. Heat energy is coming from the surrounding into the ammonium nitrate. So obviously the water is going to get colder because the heat is coming from it into the ammonium nitrate. Okay? Heat is getting out of water, so it gets colder. So it's going to be correct. The water gets colder. Always remember, during endothermic, the reaction mixture is going to get colder. During exothermic, the reaction mixture is going to get warmer. Okay, thermal energy is absorbed by the ammonium nitrate from the water. That's extremely correct, because thermal energy is going to get into this ammonium nitrate from the water. Just think of it like this. So 1, 2, 3, all are correct. Hydrogen reacts with oxygen to produce water. Okay, that's correct, and that's exactly what happens in your hydrogen oxygen fuel cell. And this reaction is extremely exothermic. It releases a high amount of energy. Some bond energies are shown. Okay, now what do we have to calculate using the data in the table? What is the enthalpy change for the reaction? Okay, let's calculate it. So now you have to understand 2-3 things that are going to happen over here. The first important thing is that you have to identify the arrow. Okay, now what do I mean by arrow? You have to identify that before the arrow, all the things that you have, this thing and this thing, what's happened? Bonds are being broken. And you should realize that after the arrow, all the things that you have, bonds are being formed. So to break these bonds, what do you have to do? You have to give it energy. So energy is going to go into this thing. And over here, energy bonds are being formed. Bond forming is exothermic. So energy is going to come out after the arrow. The energy is going to come out of the thing. Okay, so after that thing is identified, you got to realize how many bonds you have. You have one HH bond and one HH bond. Makes a total of 2 HH bonds. So 2 times my HH bond is 436. So 436. And my one O double bond is right here, which is 496. So plus 1 times my 496 is going to give me the total energy before the arrow. Okay, I get the total energy before the arrow. Let's calculate it. 436 times 2 plus 496. Okay, 436 times 2 plus 496, that's going to give me 1368. 1368 is going to be the total energy that's going in. Okay, that's going in. Now I have to calculate the energy that's coming out, and I have to subtract that energy. Okay, now energy coming out, I have one OH bond over here. Okay, you need to clearly see this thing because it's very important. Over here you have one OH bond over here and one OH bond over here. So in one water molecule, you have 2 OH bonds, one over here and one over here. This O is bonded one time over here and one time over here. So total 2 bonds of OH over here. So 2 bonds of OH. OH is my 463. OH is my 2 times of 463. And then again, in the second water molecule, you have 1 OH over here, 1 OH over here. That's going to make it 2 times 463, a total of 4 times 463. So let's get it. 4 times 463, and that's going to give me 1852. Okay, 1852 is the energy that's coming out. And what did I told you? You have to subtract this energy, 1852. So 1368 minus 1852. Okay, 1368 minus 1852, negative 484. Okay, negative 484. I get it in option C, and that's going to be my correct answer. Moving on, silicon chloride SiCl4 boils at 58 degrees Celsius. What does this tell you about silicon IV oxide? Not silicon IV oxide, it's silicon IV chloride. But what does this tell you? It tells you that it is going to be a simple molecular substance. Why it's going to be a simple molecular substance? Because it has a low melting point. Which row shows the type of change when silicon IV oxide boils and the explanation? Okay, now remember that in a simple molecular substance, what's happening is, okay, now I'm going to draw the silicon IV oxide over here. This is one molecule of silicon IV oxide. It has one silicon and 1, 2, 3, 4 chlorines. Okay, Now I am just going to copy it. You have another silicon IV oxide, you have another silicon IV oxide, you have another silicon IV oxide, and another silicon IV oxide. Okay, now we have a lot of silicon IV oxide, and now what's basically happening is you need to understand one thing. Look over here, this is a covalent bond, okay? Between silicon and chlorine you have a covalent bond, and that's something we are all sure about. But what is the problem? Why do you have a low melting and boiling point in silicon IV oxide? Why? If you have strong covalent bonds. The problem is when you are melting silicon IV oxide, you're not breaking these bonds. These bonds are not getting broken. What's getting broken is these forces. These are connected to each other. This one molecule connected to the other molecule. This force, this weak IMF between these two molecules is getting broken. These bonds between silicon and chlorine are not getting broken. What's getting broken is this intermolecular force between two molecules, the force of attraction. This is getting broken. Okay, you need to understand this. That's why it has a low melting and boiling point, because the covalent bonds need to be melted at extremely high melting and boiling point. So you cannot break covalent bonds at 50. Okay, at 58 what you're breaking is the force of attraction. Okay, type of change, melting. Okay, what you're doing is you're melting. So what do you guys think? You're boiling something. So what do you guys think? Turning a gas, boiling simply means turning a liquid into a gas. Okay, so turning a liquid into a gas, are you changing the chemical bonds? Are you doing anything? That's just a physical change. Okay, so that's going to be a physical change, and what you're breaking is basically your intermolecular force of attraction, not the bond. That's very I guess the concept that's most misunderstood is this one. Okay, moving on. A 2-gram sample of calcium carbonate reacts with dilute hydrochloric acid as shown. Okay, the important thing is you have 2 grams of sample, that's the mass of calcium carbonate. What change in the conditions make the reaction proceed more slowly? Okay, now you need to slow the reaction. Okay, so you should simply know the conditions for the rate of the reaction. Increasing the acid concentration, that's going to increase the reaction. Increasing the size of the solid particles, because when you increase the size, that's going to be correct. What happens is when you have a large particle, you have a less surface area. This blue is the surface area of the particle, but when that particle is in its powdered form like this, you have a large number of particles. The surface area of the particles increases. Let me show it to you guys. Look, now you have a large number of particles. These are the particles, and what basically happens is the surface area of the particles increases. Now the blue surfaces are going to be much more. Right over here it's just a single surface, but now outside all particles you're going to have these blue surfaces, so the total surface area increases, and hence the frequency of effective collisions increases. Increasing surface area, that's going to increase, not decrease. Increasing temperature is also going to increase. So excess aluminum reacts with dilute hydrochloric acid. You got to realize you have your aluminum in your excess, and HCl is going to be the limiting reactant. Okay, that's a good equation, and the thing that you always have to look for in equation is this part, the molar ratio. You know why you are given with the equations? Because of this thing. So you can look at how many moles going to react with how many moles. Okay, the hydrogen given off is collected in a gas syringe. The total volume of hydrogen gas syringe is recorded every 2 minutes. The result of the experiment as shown. Which statement is correct? The mass of aluminum added is this. Okay, let's see about it. Okay, how many volumes of hydrogen we have in total? We have a total of 143 cm cube of hydrogen, and aluminum is in excess. Okay, always remember, you can never determine the amount of your excess reactant. Okay, excess is something that we don't consider because it's an excess. There's a large amount, there's a lot of unreacted aluminum, so you cannot figure out the volume or the mass or anything of the excess reactant. So definitely not statement A. We cannot figure it out until and unless we have some concrete information, how much it reacted or how much did not react, then we can figure it out. Option B, the mass of aluminum added cannot be determined from the information. That's correct. That's extremely correct. You cannot determine the mass of aluminum because it's an excess. The highest rate of the reaction is this. The highest rate of the reaction is when the acid concentration is the highest. Okay, acid concentration is the highest. We honestly, I guess these statements, we just figure out the correct one. That's B. Let's not confuse ourselves with this. If you just can calculate the rate is basically the difference between these two divided by the time taken. I guess I'm sure these are not going to be correct because this one's the correct one. Okay, let's move on to this. I guess there's a lot of mole work in this thing, in this paper, a lot of moles. Okay, 157.75 of bismuth chloride is used to make 500 cm cube of solution using distilled water. Okay, that's the mass, I guess, of bismuth chloride you have, is used to make, that's the volume you have. Okay, the aqueous bismuth chloride slowly becomes cloudy as it reacts with water to form insoluble BiOCl. Okay, now we are getting cloudy because we are forming this thing. The reaction is reversible. That's the reaction. In a reversible reaction, the important thing is the exo or the endo thing. Which statement is correct? The initial concentration of bismuth 2 chloride solution is this. Okay, let's find out the concentration. We first need to find the moles of bismuth. We are given with the mass, okay, and over here we're given with the volume. So with the mass, let's find out the moles. So moles equals to mass, which is 157.75 upon your MR. MR of BiCl3. Let's figure out the MR for Bi, and for chlorine we know it's 35.5 for Bi. What do you guys think? Okay, let's check you guys. What do you guys think? What should we take for the MR? 83 or 209? Figure it out yourself. It's gonna be 209 because that's the mass number, and this one right here is your proton number. So it's gonna be 209. That's you are gonna take for your MR. So the MR is gonna be 209 bismuth and chloride 3 times 35.5. Okay. 209 plus 3 times 35.5, that gives me 315.5. So 157.75 upon 315.5, 157.75. 157.75 divided by 315.5, that gives me 0.5 moles. 0.5 moles divided by the volume, which is 500 cm cube, but we always take the volume in dm cube, so we're going to take 0.5. That gives me 1 mole per dm cube concentration of my bismuth chloride. So I guess that's going to be the correct option. Okay, true. And option number 2 says at equilibrium the rate of the forward reaction equals to the rate of the reverse reaction. That's correct. At equilibrium, your forward and your backward reaction happens at an equal rate. Third option, when more HCl acid is added, the position of the equilibrium moves to the left. Okay, let's see over here what's happening. You are adding more of your HCl thing. Okay, when you add more HCl to decrease the concentration, okay, whatever you try to do, the equilibrium tries to reverse it. Okay, you increase the concentration of HCl to decrease it, equilibrium will move towards that side. So in reality, equilibrium will indeed move to the left, because whatever change you do, equilibrium tries to reverse it or do the opposite change. So this is going to be correct, that when HCl acid is added, the position of the equilibrium moves to the left, and this is all correct. And we just didn't look below, we were given with the ARs, but it's good we checked out from the periodic table. Moving on to question 20, which says the flow chart shows some of the processes and the reactions in the formation of ammonia. Okay, we have air, then we have substance 2, we are making ammonia out of it. We have substance 1, process X. Okay, what do you guys think? What's basically happening over here? I guess to make ammonia, what do we need? We have hydrogen, and what else do we need? We need our nitrogen. And how do we get nitrogen? Air is 78% nitrogen. We get nitrogen by the fractional distillation of liquid air. And substance 1, how do we get hydrogen? By cracking of cracking of our long chain alkanes, not alkenes. We don't crack alkenes, we crack alkanes. Please learn it. We crack anes, not enes. Okay, so this is gonna be my substance 1 is gonna be my long chain alkanes. Okay, there's enes over here to confuse you. No enes, only anes. It's gonna be, the process is gonna be cracking, I crack it, and my substance 2 is gonna be nitrogen. That's simple, option A. Many reactions involve oxidation and reduction. Which statement is correct? Okay. Acidified manganate VII ions change color from colorless to purple. No. From purple to colorless when reduced. Okay, so that's incorrect. All reactions that involve oxidation also involve reduction. Let's check about it. During a reaction, oxidizing agents lose electrons. Okay, oxidizing agents get reduced. And when something is reduced, they basically gain electrons, so not lose. If it was a reducing agent, it would lose electrons. Reduction is the loss of hydrogen from a compound. Remember that reduction is not the loss, reduction is the gain of hydrogen from a compound. So it is going to be option B, that all reaction that involve oxidation also involve reduction. Because look, what is oxidation? Try to think about it in such a way that what is oxidation? Oxidation is loss. When you lose electrons, something has to gain it. Okay, you cannot just lose electrons to the environment. If something is losing electrons, something has to take those electrons. So that's why reduction and oxidation happen in a simultaneous way, and they happen in a redox. That's the reactions are called redox, because when something loses something has to gain those electrons. The equation for the reaction is shown. Which statement about the reaction is correct? Okay, let's see the oxidation states over here, because I know it's going to be something related to oxidation. Chlorine, elemental form, something is an element, has an oxidation state of 0. Bromine has a -1. It's not bromine, it's bromide over here. Chlorine over here -1, and bromine over here 0. Okay, which statement about the reaction is correct? Bromide ions are the oxidizing agent. Let's figure it out ourselves. So chlorine from 0 to -1, what's that? That is, I guess, for sure reduction. Chlorine is being reduced, and what substance is being reduced is the oxidizing agent. Okay, and now let's figure out for our bromine. Bromide ions from -1 to 0, a decrease in oxidation number. So not a decrease, that's an increase. Sorry, from -1 to 0, that's an increase. You are increasing, so that's going to be oxidation. And the substance that is basically undergoing oxidation itself is a reducing agent. So bromide ions are oxidizing agent? No, they're reducing agent. Bromine is the reducing agent, not bromine. It's bromide ions. These are ions over here. Okay, you need to understand. Chloride ions are the reducing agent. No, they're the oxidizing. So chlorine is the oxidizing agent, and that's the correct answer. Moving on to the next question, which says, which row describes both? The pH. Okay, the first thing that we need to look for is the pH, and the ion with the greatest concentration in an aqueous alkali. Okay, I guess that's easy. We know that alkalis have a pH which is greater than 7. So an alkali should have a pH that's greater than 7. So that should be this one, A part, and B part. It should be greater than 7, take care. And acids have a pH less than 7. And the ion which makes an acid is this H plus ion, and the ion which makes an alkali is the OH negative ion. I guess that was pretty easy. It had to be option B. Moving on, the water in a lake is acidic and the fish are dying. Okay, so that's a problem, that you have acidic water and your fish are dying. The water in the lake needs to be neutralized so that the pH is close to 7. Okay, now the problem is that, for instance, you have an acid. Okay, the water is acid and you need to neutralize it. So what are you going to add to the water that's going to neutralize it? Obviously, you need to add an alkali to an acid, so you neutralize it. Which compound is added in excess to neutralize the water in lake? Okay, you have to add it in excess. Okay, now we have phosphoric acid. Why would you add acid to an acidic lake to neutralize it? That's complete nonsense. So not at all. Potassium hydroxide, okay, that's an alkali. sodium nitrate. Why? Sodium nitrate is a salt. It's not an alkali. Why would you add sodium nitrate? It would just become more salty. Never. So now the two options are option C and option A. Okay. Now both of them have the capacity to neutralize an acid. Calcium carbonate gonna neutralize the acid to form a calcium salt, to form carbon dioxide, because that's a carbonate plus acid, salt, carbon dioxide and water. And potassium hydroxide is going to form salt and water. Now if any one of you can think which are we going to use. Okay, I'm going to tell the correct answer, which is A. And why A, not C? Because potassium hydroxide is an extremely, I would say, strong alkali. It has a pH close to 14. That's an extremely high pH. We can not use potassium hydroxide because look, we are adding the alkali in excess. What do you want? If it's not acidic, if you don't want an acidic water, do you want an alkaline water? No, because you're adding in excess. You cannot add excess of such a strong alkali. All the fish, they're going to eventually die because of this potassium hydroxide, extremely alkaline. So you prefer rather a kind of a neutral option which won't increase the pH too much. Okay? So that's why you use calcium carbonate to neutralize it, because it's not a very strong kind of a solution. Moreover, one important other thing is that potassium hydroxide is extremely soluble in water. It's all going to dissolve, whereas calcium carbonate is less soluble. So even if you add some in excess, all of it might not dissolve because it's partially soluble. So that's what you need to keep in mind. That's why that's a very good option, because it won't harm the fish that much. Moving on to 25, it says, which pair of reagents is used in a school laboratory to prepare a sample of pure barium sulfate? So now the thing that you need to realize over here is that barium sulfate is an insoluble salt, and to prepare an insoluble salt, you need to take two soluble salts. I always write this something like this, that soluble plus a soluble forms a insoluble salt. So you need to take two soluble salts to prepare an insoluble salt. Okay? First, whenever you're preparing a salt, you need to look at the solubility rules. Okay, you need to look at the solubility rules. Insoluble, so that means we're going to use two soluble reagents. Okay, one reagent should have barium, one should have sulfate. For barium, can we use barium carbonate? No, barium carbonate is insoluble. We need soluble. Can we use barium carbonate? No, insoluble. Barium chloride, yeah, it's soluble. Barium chloride is soluble, so we can use it. Barium hydroxide, insoluble again. All chlorides are soluble except for lead and silver. So barium chloride is soluble. And sodium sulfate, yeah, it's soluble. All sodium salts are soluble. So we have our two soluble reagents, which are going to be barium chloride, which is soluble, and sodium sulfate, which is also soluble. I guess that was easy. Moving on to the next, which says the total number of electrons in one atom of element Q is this. So now we're not talking about the electrons in the last shell. What we're talking about is the total number of electrons in one atom of an element is 17. Can you guess what that atom is going to be? No, you cannot guess. Why you cannot guess? Because electron does not tell you about the identity of the atom. What tells you about the identity is the proton number. So if you have the proton number, you can tell which kind of atom it is. So 17 cannot tell you because it might be an ion or something else. In one atom of element R, okay, in one atom of element Q, it's 17, and in one element of atom of element R, it's 19. Which statement about element Q and R is correct? Okay. Q and R react together to form a covalent compound. Q and R form positive ions. Okay. Now one thing important over here. What we're talking about is not an ion. We are talking about an atom. An atom means that it's not an ion. It has not lost electrons. It has not gained electrons. It's going to have equal number of protons and electrons. Okay? And over here, we are also talking about an atom. So that means that what we can consider over here is that 17 is going to be the number of electrons as well. This is the electron number, can be the number of protons as well. And 19, same, can be the electron number, can be the number of protons as well. So we got to look for an atom in the periodic table that has 17 number of protons, and another atom we have to look that has 19 number of protons. So here we go with our periodic table. 17 we have chlorine, then we have 18 which is argon, and 19 is potassium. So we have chlorine for 17 and potassium for 19. So a chlorine is a 17 and a potassium is a 19. So now I guess that's a perfect match because it's K plus, Cl negative. Because it forms a negative ion, we can easily form KCl, a very strong ionic bond we can form. Okay, Q forms positive ions. What is Q? Q is this. Q is what we just identified it to be chlorine. Does it form positive ions? No. According to me, it forms a negative ion. R has more outer shell electrons than Q. Okay, no, R is potassium. K plus 1 ion, that means outer shell has 1 and it loses 1. So R does not have more, R has less. Whereas this chlorine, it has 7 outer shell electrons. It just need 1 more to get stable. Okay, so that's why it has a charge of negative 1. R is more metallic than Q. Oh yeah, potassium is more metallic than obviously chlorine because it's a metal. That's going to be correct. R is going to be more metallic. Okay, moving on to question number 27, which says that which statements about group VII? What do you mean by VII? V means 5, III means 5, 6, 7, 8. So that means we are talking about group 8. Noble gases are correct. They're unreactive. Okay, all of you should know they're unreactive because they have full outer shell electron. They do not lose electrons. They do not gain electrons because they're full. Okay, they have a full outer shell of electrons. Okay, that's also correct. They are diatomic gases at RTP in pressure. That's completely incorrect. They are not diatomic. The word you use for your noble gases is monoatomic. So they are monoatomic gases. Hence, making option 3 incorrect. It's going to be 1 and 2, which is going to be option B. Okay, iron has a high melting point. We all know that. But why do you guys think iron has a high melting point? Because iron is a transition element. Not if you don't even think about transition element or transition metal, you only think that iron is a metal, you'll get why it has a high melting point, because it has strong metallic bonds. A metal has a high melting point because it has strong metallic bonds. A ionic compound has a high melting point because it has strong ionic bonds. Simple, because of the strong metallic bond. And what is a metallic bond? What do you guys think is a metallic bond? Simple. You have a lattice, you have your positive ions. This is iron. Okay, I'm making iron. This is a lattice of iron. You have your positive ions. Between positive ion, you have your negative electrons. These are your delocalized electron, and between these positive ions and this electron, there's a force of attraction. Okay, there is attraction. Both of them attract because they're opposite. Positive, negative attract. There's strong electrostatic forces of attraction between the positive and negative ions. That's why iron has high melting point because of these forces. Okay, which statement explains the high melting point? Each iron cation. Okay, do you think cation is the correct word? Okay, let's see. Has a strong electrostatic attraction to a sea of delocalized electron. Okay, that kind of explains the thing. Okay, we have strong attraction, but let's read the other statements as well to be on the safe side. In every iron atom, iron does not have atom, it has ions. These are ions, these are positive ions. In iron lattice, you don't have atoms, you have ions, because the atoms have lost their outer shell electron. This outer shell electron from the iron atom, this is iron, has gone out, hence it's formed an ion. Okay, that's incorrect. Iron has the same structure as diamond. Oh my god, how is this possible? Diamond is a completely different structure. Diamond has covalent bonds. Iron has metallic bonds. Iron is an alloy. How can iron atom be an alloy? Stainless steel is an alloy. You make alloys out of iron, but iron itself is not an alloy. This cation word seemed a bit fishy right here, but I guess that makes sense because cations are just, your positive ions. So you have positive ions and you have these electrons and you have a strong attraction between them. That's why you gotta have high melting point, because what you have to break when you're melting iron, you have to break this attraction between these electrons and these positive ions. When you're breaking ionic bonds, when you are trying to melt an ionic compound, what are you breaking? You're breaking the attraction between the positive cations and the negative anions. Over here, you're breaking this attraction. So that's what explains the things. Which statement about alloys is correct? Alloys are not electrical or thermal conductor. That's incorrect. Alloys are indeed good electrical and thermal conductors because they are made up of metals. Okay? Because they are made up of metals. Alloys are softer than pure metals. They are not softer, they are harder than pure metals. Brass is a mixture of copper with small amounts of chromium, nickel, and carbon. That's incorrect. Brass is made up of copper and zinc only. The percentage of each metal in an alloy may vary. That's extremely correct. Because remember that whenever we are making mixtures, okay, an alloy is a mixture. An alloy is a mixture of metals. Whenever we are making mixtures, the ratio is not fixed. For example, that's why I said that mixtures cannot have proper formulas. Why? Because the ratio can change. In a compound, for example, if you're making a compound, calcium chloride, you should have a fixed amount of calcium and chloride to make this. But for a mixture, you can add variable amount of calcium and variable amount of chlorine to make it. So the things can vary in a mixture. Okay? And alloys are just mixtures of your metals with other elements. Okay, question number 30, which says the table shows the reactions between four metals P, Q, R, S and their oxides. Okay, the oxides of metallic oxides are, you should know this, metallic oxides are your basic oxides or your amphoteric oxides. That should be known by you guys. And your non-metallic oxides can either be your neutral oxides or your acidic oxides. Okay, reaction with water. P reacts only with steam. Q does not react. R does not react, and S reacts rapidly. Okay, reaction with, then we have dilute acid, and then we have reaction with carbon. Okay, let's see. What is the percentage? What is the order of reactivity for the most reactive to the least reactive metal? Okay, we know that what reacts rapidly. First, let's figure out from this water thing. What reacts rapidly should be the most reactive. So, what is the order of reactivity? S should be the greatest. After S, it should be this P thing because it reacts with steam, at least better than not reacting. So, after that, it's going to be steam. Okay, the first thing we figured out was S. The second thing we figured out after that, it's going to be reacts with steam. After that, either we have Q or R. Let's see with acids. Okay, this reacts rapidly. This reacts rapidly. Okay, Q reacts slowly. So R does not react. So Q is stronger than R because at least it reacts slowly. R does not react at all. So after that, we should have Q and then we should have R because Q reacts slowly and R does not react. So after that, we have our Q and then we got to have R. So that makes it to be option C. Moving on, which reactions take place during the extraction of aluminum from aluminum oxide using carbon electrodes? Okay, first of all, the first mistake, just by looking at it, aluminum does not have a charge of 2+. Aluminum has an oxidation state of 3+. Okay? So just let's cross out this. Second thing is that, is this correct? Okay, you have two oxide ions and basically you're forming an oxygen and you're losing 4 electrons. That's correct. Okay, then the oxygen that you just formed right here, that's reacting with the carbon in the anode because look, which kind of anode you're using? You are using your carbon electrodes. Okay? The anode is going to be made up of carbon and at the anode you're going to form oxygen. Okay, so the oxygen that's being formed at the anode reacts with the carbon that's present in the anode together, from which the anode is made up of, to form CO2. So these two reactions take place, 1, 2. And that's why in the electrolysis of aluminum oxide, what happens is that you need to replace your anodes regularly because the carbon in the anode basically reacts with the oxygen and your anode gets eaten up or is like just turns into carbon dioxide, is lost. So you need to replace it regularly because of this carbon in the anode reacting with the oxygen. So it's going to be 1 and 2, which makes it to be B. NPK fertilizers. What does NPK tell us? NPK, nitrogen, phosphorus and potassium. Okay, you should know this. This is your nitrogen. This P is for your phosphorus. All these are essential compounds, elements for the growth of the plants. And this is your potassium. Okay, solid NPK fertilizer has the properties listed. Water soluble, obviously it has to be water soluble because it have nitrates. You cannot directly put nitrogen into soil for plants to absorb. Plants can't directly absorb nitrogen, otherwise they would have just taken the nitrogen from the air. Air is 78% nitrogen. Why don't plants simply take up the nitrogen that's 78% in abundance inside the air? Because plants can't just directly take the nitrogen. They need nitrate ions to get absorbed through their roots. So that's the concept over here. So that's why you add fertilizers. And moreover, you need some bacteria, some nitrogen fixation bacteria in your soil that's going to turn the nitrogen in the air into nitrate ions inside your soil. Okay, that's some biology. Moving on, has an aqueous solution with a pH of 7. Okay, you need pH 7. That means it's neutral. Okay, which substances are mixed with the mixed to make a solid NPK fertilizer? Okay, you need to make a solid NPK fertilizer. Ammonium nitrate, potassium sulfate, and phosphorus oxide. Okay, the thing over here is that I cannot take phosphorus oxide. Why cannot I take phosphorus oxide? I need to have a pH of 7. I know phosphorus is a non-metal, and non-metallic oxides I know are acidic. So if I take phosphorus oxide, my pH is going to reduce from 7. So I cannot take this thing. Second thing, ammonium phosphate. Okay, that's gonna give me, ammonia is gonna give me my nitrogen, phosphate is gonna give me my phosphorus, and potassium hydroxide. Again, I cannot use this because I have this potassium hydroxide. I cannot take potassium hydroxide. That's gonna increase the pH from 7. I need a pH of exactly 7 for this fertilizer, so not this option. Okay, moving on to my option C, which says ammonium sulfate. Okay, that's adding sulfate ions as well. Okay, calcium nitrate. Okay, and sodium phosphate. We have 3 different types of salts over here. But look, along with these salts, okay, from this salt, I'm gonna get my ammonium. Okay, I need my ammonium. Why I need ammonium? Because ammonium has this nitrogen in NPK. Second thing, from this, I need this nitrate thing, because this nitrate thing also has nitrogen. And from the third, I need this phosphate thing, because this phosphate thing going to give me my phosphorus. But one thing still I don't have, which is my potassium. I need my potassium as well, this K thing. So that's why I'm going to use the last one, which has everything. It has potassium nitrate, which this potassium is going to give me my potassium thing. Nitrate is going to give me my nitrate ions, NO3 -1, and this phosphate is going to give me my phosphorus. So that's why I am going to go with my option D. So that's the thought process behind all of this thing. Moving on, alkanes are saturated compounds. Okay, we know alkanes are saturated. Why are they saturated? Simply because they have carbon-carbon single bonds containing carbon hydrogen only. Okay, alkane should not have anything apart from carbon and hydrogen. Structures 1, 2, 3, 4 are saturated hydrocarbons. Okay, which pair of structures are isomers? Okay, what are isomers? Isomers are compounds that should have technically the same molecular formula. The molecular formula or the number of atoms, they should be same, but the structural formula should be different. Structural formula should be different. So let's see and count the number of atoms to see which have the same molecular formula but different structural formula. Okay, the first alkane that I get, let me count the number of carbon, which is 1, 2, 3, 4, 5, 6, 7. Okay, that's C7. This one is 1, 2, 3, 4, 5, 6. This one is C6. Okay, this one right here is 1, 2, 3, 4, 5, 6. This one right here is also C6, and the last one is 1, 2, 3, 4, 5, 6. Okay, so this one is also C6. Okay, now the next thing I need to look at is my okay, the next thing that I need to look at is my hydrogens. Okay, now this comes out because it has C7 and none of them have C7, so it cannot be an isomer of anything. Okay, now counting hydrogens. I have to be proficient at this because even if I mess out one hydrogen, everything's going to be destroyed. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay, H14. Now for this one, I know technically that's going to be 12, but still I'll count because for the sake of simplicity, we should count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, H12. And this one is going to have H14. So what do you guys think? What are isomers over here? We have 1, 2, 3, 4, 5, 6, and 14, and H14. Okay, structures 2 and 4. What do you guys think about them? Are 2 and 4 isomers? Okay, now comes a different concept over here. Okay, now one thing we know that 3 cannot be an isomer of this or this because they have different molecular formula. This is C6H14, this is C6H12. 14 and 12, this is different molecular formula. So now we cross out another option, which is option number 3. So we're left with only 2 and 4. So obviously it has to be D, but let's understand why it's D. Okay, now I know that over here this branching, this carbon is a branch. So my branch is on the 1, 2, 3rd. On my 3rd carbon is my branch. So this becomes 3-methyl, and because it's going to be 5, 3-methyl pentane. Okay, this becomes 3-methylpentane. You don't need to learn this, but the branching is on the 3rd carbon. Over here the branching is, if I start from here, because you always start from the carbon from where the branch comes nearer. Over here the branch is going to come 1, 2, 3, 4. Over here branch comes at the 4th one, so I'm not going to consider from this side. Instead I'm going to start from the right one because the branch over here is on the 2nd carbon. So this becomes 2-methylpentane. So 3-methylpentane and 2-methylpentane are going to be isomers, because they have the same molecular formula, C6H14, but different structural formula. So 2 and 4 are the isomers. Which statement is correct? Any compound that contains both hydrogen and carbon is a hydrocarbon. Contains both hydrogen and carbon. Okay, now I'm going to give you an example. I have a glucose molecule which is C6H12O6. Can any one of you tell me that either it's a hydrocarbon or not? That's going to be a challenge. Let's see. Okay, let's first read the other statements, and meanwhile you guys think about, is it a hydrocarbon or not? Okay, petroleum is a compound formed from many different hydrocarbons. Okay, is it a compound? Do you guys really think that petroleum is a compound? I don't. It's a mixture. It's a mixture of different compounds. Okay, the boiling points of hydrocarbons increase when the chain length increases. Oh, okay. That's a good statement. The boiling points of hydrocarbons increase as the chain length increases. Look, your carbon atoms are increasing. So what basically happens is, as the number of carbon atoms in the chain increases, look, C6 only has 6 carbon atoms, whereas C50 has 50 carbon atoms. The chain length increases, so the forces of attraction also increases. The van der Waals forces. This is the name of the forces. The van der Waals forces of attraction increases. So the boiling and melting points increase as the chain length increases. The naphtha fraction obtained from petroleum is used for making roads? No. It's used for making chemical feedstock, and for making roads you use bitumen fraction. Okay, now coming back to statement 1, this is not a hydrocarbon. A hydrocarbon contains carbon and hydrogen only, but over here glucose molecule, it also has this oxygen. A hydrocarbon should only have 2 things, carbon and hydrogen, nothing apart from it. So the word only is missing from here. Any compound that contains both hydrogen and carbon is a hydrocarbon? No. There should be carbon and hydrogen only is going to be a hydrocarbon. If you have anything apart from carbon and hydrogen, it is not a hydrocarbon. Okay, this glucose is not a hydrocarbon because of this oxygen. There only one condition, that means for a hydrocarbon, that means nothing apart from carbon and hydrogen. Moving on, compound Q is a hydrocarbon that has no structural isomers. Okay, we cannot have any isomers. Compound Q does not decolorize bromine and dark. Okay, does not decolorize bromine, that means it's not an alkene, because alkene decolorize bromine and dark. So it cannot be an alkene. C4H8 is an alkene. C3H6 is an alkene. It can either be this or this. What is compound Q? Oh, that's so easy. It's obviously going to be B, because C3H8 has no structural isomers. Because look, let me show you. You might think C3H8 has a structural isomer. Let me show it to you guys. Look, 1, 2, 3 carbons in a straight chain. Now I decide, okay, and these are the hydrogens, okay? I am not writing H, but just consider them to be the hydrogens. Now I decide that I need to make an isomer of C3H8. What do? I take this carbon and put it over here down and try to make a branch out of it like this. C, C, and a branch over here. But while making this branch, what I did was I just tilted it. Now it became like this, but still it's not branched, because now I'm going to start my counting from here, and if I try to join all the carbon atoms with a single pencil, I can still join them. Branching is when you cannot join all the carbon atoms with a single flow of pencil. For instance, this is a branch. Look over here. This is a branching. This carbon right here is a branching, because when I try to start my pencil from here, I try to join. Over here I get two junction. Either I can go towards here or down. I decide to go here, then I need to bring back my pencil and join this. I cannot join in a single go all of them. Or if I decide to go down, then I need to bring back my pencil here and join. So that's how I know this one's a branched, and over here I can join all in one go, so that's not a branch. So C3H8 does not has any structural isomers. Which equation represent reactions of alkanes? Okay, so we are looking majorly for substitution reactions. Okay, you have CH4, you add chlorine to it, you form CHO. Many of you might think one thing, that this thing is possible. Please, this thing is not possible. At a time, remember that you can only and only replace one hydrogen atom. Over here, this chlorine replaced two hydrogen atoms. C4 से दो hydrogen atoms replace करके C2 बना दिया, और दो chlorines एक time पे अगर hydrogen gas बाहर निकल गई. This is impossible. At one time, you can only replace one hydrogen atom and you form HCl, not hydrogen gas. So reaction 1 is not possible. Okay, you need to understand this. Okay, moving on to reaction 2, which says that you have C2H6 plus 5O2, and then you are forming this. Okay, that's a simple, I guess, reaction of a simple combustion reaction. That's possible. Okay, a combustion is possible for alkanes. Over here again, same mistake. This hydrogen, please remember, this hydrogen cannot be formed. You need to form HCl. Okay, at a time, this is not possible. How you're adding HCl to it and replacing it? Impossible. This is all nonsense. Okay, so I guess the only correct option, I don't guess, I'm sure it's going to be 2 only, because this one's possible. H2 cannot be formed. You need to form HCl. Okay, ethanol is produced using either ethene or glucose. Okay, you know what you do with ethene. You do catalytic addition of steam at 300 degrees Celsius and 60 atmospheric pressure, and you use H3PO4 as your acid catalyst. And for glucose, the conditions you should know: 25 to 35 degrees Celsius temperature. You need your yeast, you need your anaerobic conditions, and you form ethanol and carbon dioxide gas. Okay, starting material for ethene is going to be catalytic addition of steam at 300 degrees Celsius and 60 kilopascals. Okay, now one thing over here is that you need to know that you're taking 60 atm. Okay, now you don't know your pressure in kilopascals, but it's fine, because over here this is wrong, so you know that it's going to be 6,000. Okay, but remember that 1 atm equals to 1,000, not 100 kilopascals. Okay, it's going to be equal to 100 kilopascals. Learn this, that 1 atm going to be equal to 100 kilopascals. That might help you, that 60 atm equals to 6,000 kilopascals. So this one's correct, I guess. A is correct. Okay, 135, that's incorrect. 35, in the presence of yeast and oxygen, use anaerobic conditions, you cannot have oxygen. Okay, the diagram shows 4 pieces of apparatus that are used to measure the volume of a liquid. Which piece of apparatus is always filled to the same level? Obviously a pipette, always filled to the same level, because there's a fixed mark of 25, or you can say 50 cm cube over here, and you fill it to that fixed mark. Okay, because that's the only volume you have on a pipette. Only one mark on the pipette, that's this. A gas range has several marks. You can add any volume of gas. A burette, you can add any volume. A measuring cylinder, you can add any volume. But for a pipette, you need a fixed volume. So it's always filled to the same level. Okay, the chromatogram shown is produced using a spot of black ink placed at point X. Okay, you placed a spot of black ink, and this is what you got. That's your solvent front, that's your baseline. Okay, spot M is produced by the blue ink, blue dye in the ink. What is the RF value of the blue dye? Okay, and over here you don't have to use your own scale because you're given with a scale. Okay, what do you have to look? You have to look for this distance from the baseline to the solvent front. Okay, what is this distance? From 4 to 16. That's going to be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this total distance from the baseline towards this solvent front is 12. So 12 upon, what is the distance for point M? This is 1, 2, 3, 4. It is 12 upon 4. So not 12 upon 4, 4 upon 12. This distance that is traveled by the substance is above, and the distance that is traveled by the solvent front is below. So it's basically 4 divided by 12. That gives me 0.33. Okay, 0.33. That's going to be option C. Okay, always remember that your RF value cannot be greater than 1. Okay, if you get an RF value that's greater than 1, you should know that you have done a mistake. So it can never be greater than 1. Okay, the table shows the result of a series of tests with two substances X and Y. Okay, these are the tests, and that's why I always say learn the qualitative analysis thing. You might be tested for it. In P1, which row shows the identities of the ions present in X and in Y? Okay, you add nitric acid, no reaction, no reaction. Then you add aqueous silver nitrate white precipitate. That means this X thing contains a chloride ion. Because a white precipitate, if you have learned the qualitative analysis, you should know what I'm talking about. So it must definitely have a chloride ion. Okay, and this one does not have a chloride ion. This Y thing does not have a chloride ion because no precipitate. Okay, you add aqueous sodium hydroxide. You get a white precipitate insoluble in excess. Okay, a white precipitate that is insoluble in excess, and you get no precipitate. That means no calcium ions in this and calcium ions in this, because only calcium ions are insoluble in excess. Then you add aluminum foil, added, warmed gently, no gas produced, ammonia produced. That means that's going to have a nitrate ion. And then you have a flame test, and you have orange red flame for here. That confirms the presence of calcium ions over here. And over here you have a yellow flame, that's sodium, and you have nitrate from this ammonia thing and sodium from this thing. So that's going to make it option D. I hope you liked the video. Do subscribe to the channel, and that's going to mean a lot. And thanks for watching the video. Bye bye.